Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel, and it also really helps us reach others in need of assistance with these topics. So what we have going on today's video is we're going to be looking at statics, and we're going to be looking at equilibrium of rigid bodies, just meaning that we're going to be looking at some reactions here, and this will be the 12th part in this particular series. So what we have going on is we have a 10-foot beam AB that rests upon but is not attached to supports at C and D. So what that means is that this beam AB is just resting here at C and resting here at D. There is no hard connection there. It's like it's just being sat down on those points. So neglecting the weight of the beam, we need to determine the range of values for P over here on the left, for which the beam will remain in equilibrium. So the trick here is to realize that because of this right here, it is not attached to, means that the reactions at C and D can only be going in the upward direction. They can only be pushing back and reacting to the forces going downward. If C and D were to be going downward, that means that they would be able to grab onto the beam and hold it in the downward direction. Well, that's not the case here. So essentially what we have to determine here is two portions. So if we have our beam that we redraw here and we have 240 on this side, and then P over here, we have to determine what value of P, oh, give me my pen back. What value of P would there be if this entire portion is balanced at point D with no regards to whatever C is, and then repeating that process and finding what value of P will balance the entire beam at C. So it's kind of like a very, very uneven seesaw here, where we want this to be nice and flat and completely balanced at point D, where P will balance out with the 240 with D, and then repeat that process and it balances out with the 240 at C. So looking at what's going on here, so how do we do this? Well, with the first portion here, if you were to sum moments at D, you could get P setting Cy equal to 0. And then the same thing with point C down here. If it's balancing at point C, that means the moments are in equilibrium, and dy would be equal to 0 at that point. So this would give me my range of P values. So let's do this. So summing moments at point D equal to 0, this meaning that we are setting Cy equal to 0 to see what that balance is, because we can't have Cy be less than 0 because that means it's going downward. Alrighty, so this is a very simplistic equation. We would have P, which would be rotating counterclockwise about D, so it's positive P times its total distance to D, which is the 3 plus 5, which is 8 feet. And then we would have the 240 going about D, and that would be going clockwise, so it's minus based upon my sign convention. And it's 2 feet away from point D, and essentially that's all we have. So my P would just be 240 times 2 over 8. And that would give me exactly 60 pounds. So this is one of the ranges that I'm looking for, because that's what we're looking for, is a range of values for P in which we don't flip this thing over. We keep it balanced and resting on these reaction points. So what this means is that anything less than the 60 pounds, C sub y would have to be going downward then. So what we have going on is that we found one of our range values. Now we have to find our other range values. So what we're going to do is we are going to sum moments at C equal to 0, and this would be where dy is equal to 0. So let's go here and let's sum moments about point C. So we're going from P, which will still be rotating counterclockwise. It is now only 3 feet away from C. And then we have that 240 still rotating in the same direction about point C, but now its distance has increased to 7 feet, and all that is equal to 0. Once again, pretty easy equation to solve for. So then we would have P is equal to 240 times 7, all divided by 3, and that gives us 560 pounds. So what this 560 means that anything greater than this dy would have to be pulling downward. Because if you think about it like this, thinking about these are your range values. So if P is equal to 560 pounds, this thing is perfectly balanced. And it makes sense for this portion at C. If this is 560, it's a much shorter distance away from C than it is to 240. So it has to be a lot larger force to cancel with the possible rotation of the 240 since it is further away. Now, if this 560 was greater, if it was like 561 or 600 or 1,000 pounds, my beam would end up looking like this then, with this thing being much larger, because let's just use the nice 1,000 pounds of force here. It would rotate it like this about C. Well, the 240 is not strong enough or further enough away to keep this thing in balance now. D sub y, to keep everything in equilibrium, would have to be going downward to pull it back down. So 560, that is our cap. And then same thing with 60, just in the reverse direction here. Anything lower than that, we are not in a perfect balance portion here. So this would be my ranges for my P. And that's how you would solve that problem. So I hope this video was helpful. And if you want to see more problem solved this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us out. Thank you for watching, and I hope you have a fantastic day.